This lecture is going to discuss how to find the properties of working substances. In the introduction, we saw that work and heat transfers with systems result in changes to the properties of our working substance, whether that's water, air, refrigerant, doesn't matter what the substance is. As work and heat exchanges happen with the surroundings, the properties of the substances change. So we need to find out how to find the properties of our working substances. So first of all, we're going to define the scope a little bit here. The types of substances that we're going to look at in this class are called pure substances. That means they have uniform and invariable chemical composition. So some examples of that would be water, nitrogen, oxygen. So that means as you move around in the system, the substance is exactly the same. So there isn't different substances in different parts of the system. So that's the uniform chemical composition. Invariable means it's not changing. So that means we're not looking at things like combustion. So whatever the substance is at the beginning of the process goes through a process, it's the same at the end. Also, we're going to look at simple compressible systems. That means that the only means for work exchange with the surroundings is a change in volume. So when we were introducing the concept of work earlier, we talked about different types of work exchange. Certainly mechanical work, which is work that occurs through a change in volume, is the most common one, but we also discussed electrical work being done on the system. Well, in this section of the course, we're restricting ourselves to just simple compressible systems. So the only work interaction is through a change in volume. So this leads us to the state principle. For simple compressible systems, two independent properties are required to fix the equilibrium state. So we're going to be using this fact that we only need to know two things to fix the state a lot as we go forward. Now next I want to talk about what do we mean by fix the equilibrium state. Well, essentially that means find all the properties that we need. So if we're given enough information that we can find any property that we need at that state, then that state is said to be fixed. So we'll be using that term quite a bit as we go on. So there are a lot of thermodynamic properties that we're going to be talking about, and we introduced a long list of them in the introduction to the course. But for the next little while, we're going to talk about only three properties: pressure, specific volume, and temperature. So P, V, and T. Now the state principle here says that any two independent properties are required to fix the equilibrium state. So that means we could choose, if we wanted, temperature and specific volume, and that should be enough to figure out what the pressure is. So that's what that means. Given two properties in this illustration, that's temperature and volume, what is the pressure? So P should be able to be expressed as a function of T and V. This shows pressure, temperature, and specific volume as coordinates on a three-dimensional coordinate system. So if P can be expressed as a function of T and V, like this proposes, that means that there's a surface on these P, T, V coordinates that represent all of the equilibrium states of whatever substance we happen to be looking at. So the equilibrium states are defined by a surface on these coordinates. So a lot of what we're going to be talking about as we go forward here is figuring out what is the shape of this surface. So I say a surface because if we're given T and V, like this implies, that tells us we have a particular T and a particular V. That gives us the coordinates on this base plane here, TV, and this means that for this particular substance, at any particular temperature and specific volume, there is one value of P that represents the position on this surface. So if we were to do that at a whole bunch of different values of T and V, we would plot out the shape of this surface. So it's the shape of that surface that we want to explore in the rest of this lecture. So to do that, to begin to see what this surface looks like, we're going to do a constant pressure experiment. So the way that this works is we're going to take a substance that's initially a solid, so we're just taking a block of some substance, and at this stage it doesn't matter what that substance is, and we're going to add heat to that substance while keeping the pressure constant, as the name of this experiment implies. So keep the pressure constant as we add heat to this substance. And while we're doing this, we're going to measure the temperature and the volume. So notice the three properties that we introduced on the last slide. Pressure we're keeping constant, and the other two, temperature and volume, we're allowing to vary, but we're going to monitor how they change. So a little illustration of how we might do this. This cross-hatched material down in the bottom of this piston cylinder device is the block of material that we're starting with. So that's a solid. Notice there's a little key here. The cross-hatch is solid. Later on we'll be talking about liquids, which will be blue horizontal lines, and then gas will be red diagonal lines. But initially it's a solid. Now also there's a piston here, so this thick black line is a piston's, and there's a weight sitting on top of that piston, and that weight is just a constant weight sitting on there. So the pressure inside of this solid is determined by how big that weight is. And as we add heat to this thing and things start to happen, the pressure inside of that system, in this substance, whatever it is always going to be the same. So that's how we achieve this constant pressure experiment. Now as we do this experiment, we want to monitor temperature and specific volume. Remember, this is just volume divided by mass. So whether we make this axis volume or specific volume, we're dealing with a fixed mass here, so it doesn't make any difference. Lowercase v is specific volume. So we're going to measure those two, and we're going to trace out a line of constant pressure on TV coordinates as we do this experiment. So notice our starting point down here is in the bottom left corner. So we're starting off at a low temperature, because it's a solid, and a small volume. So we're starting off down in the bottom left corner of the TV diagram. So we start to add heat to this thing. The very first thing that is going to happen, we add heat to the solid, it's going to expand. So we see the volume is increasing, and the pressure, of course, is staying the same, and the temperature is going to increase. So as we start to trace out our path on the TV diagram, and remember we're tracing a line of constant pressure, we will see both specific volume and temperature increasing. Now that temperature increase will continue until we reach the melting point of this substance. And as soon as we reach the melting point, some of this is going to start to melt. So here we see a two-phase mixture, solid down in the bottom, but a portion of it has now melted and become liquid. So we now have a two-phase mixture. Well, as we move on our TV diagram from point 1, where this is just about to start melting, and we continue to add heat, we can see that the volume certainly is going to continue to increase. So we're going to keep moving to the right here, but it turns out that the temperature stops increasing, because as we add heat to this, the temperature does not go into increasing the temperature of the system. That energy that we're adding goes into converting this substance from a solid to a liquid. So we go through a phase change, and on the TV diagram that phase change happens at constant temperature. So the temperature starts going up, and we get a flat part on this line of constant pressure. So this temperature right here would be the melting point of this substance. Now as we continue here, this is going to continue to expand over to point 2, and point 2 is when all of the solid is gone. So we've completely converted this solid to liquid, and that's point 2, completely liquid filled, and that's the end of this constant temperature portion of this line. Now if we continue to add heat to this, the temperature is going to go up again. So temperature increases and it also expands. So the liquid expands and the temperature goes up. So both V and T are increasing as we go from 2 to 3. And of course that's going to continue until we get to the boiling point. So once we pass the boiling point, again we have a two-phase mixture. We have liquid and vapor together in the container, and again there's going to be a flat part in this line of constant pressure. So this temperature is the boiling point of this substance at this particular pressure. And of course that's going to continue until all the liquid has been converted into vapor, and then after that the vapor will continue to expand as we add more heat, and the temperature then will begin to rise again. So this is a line of constant pressure on TV coordinates, and it shows two phase changes. The change from solid to liquid, which occurs at constant temperature, and the change from liquid to vapor, which also occurs at constant temperature. So this is the melting point, and that is the boiling point of this particular substance at this particular pressure. So that's our constant pressure experiment. Now what we want to do is look at what would happen if we repeated that experiment at a bunch of different pressures. So here's our TV diagram again. This is the same axis as we had on the previous slide. So the line brought forward from that looks like this. Now I need to make a point here. Notice that this phase change that I'm showing here is the phase change from liquid to vapor. I've dropped off the phase change from solid to liquid, which would have occurred down here. In this class we're just not interested in that phase change. The phases that we're going to be focusing on are liquid, vapors, and mixtures of liquid and vapor. We're not going to be dealing with solids anymore. So I'm just showing that one phase change. So this is our line of constant pressure on TV coordinates showing a liquid region, a liquid-vapor mixture region, and a vapor region. Well, we could redo that entire experiment over again at a larger pressure. So it would look the same. We just put a heavier weight on top of the piston to make the pressure in the piston cylinder device higher. And if we were to do that, we would get another line that might look something like this. And if we were to do that again, we might get another line that would look something like this. So this is a series of 3 lines of constant pressure on TV coordinates. These lines of constant pressure are called isobars. So an isobar is a line of constant pressure. Now there's some very important points along these isobars. If we look at this set of points along the left-hand side, at each of those points is where we go from 100% liquid to a liquid-vapor mixture. And this set of points along the right side is where we go from a mixture to 100% vapor. So those two sets of points are very important, and typically we would show all of those points together as a saturated liquid line, that's what that blue line is called, and a saturated vapor line, that's what the red line is called. So notice also that as we go to a higher and higher pressure, this distance gets smaller and smaller. And in fact, if we go to a high enough pressure, that flat spot disappears. And this is a special point that we'll talk about in a moment. So this saturated liquid line and saturated vapor line are two very important features to show on a TV diagram when we're talking about a substance that changes phase from liquid to vapor in the region where we're interested in using that substance. So this point at the top where the saturated liquid and saturated vapor line meet is called the critical point. We'll be talking more about the critical point in a few slides. But right now we just want to give a little more formal definition of these saturation lines because they're very important. So the saturated liquid line is 100% liquid. So if we're sitting on the saturated liquid line, we have 100% liquid. That is true. However, the addition of a small amount of heat begins the formation of vapor. So that means on the saturated liquid line, we're just on the verge of vapor starting to appear. The saturated vapor line is 100% vapor. However, if we remove a tiny little bit of heat, liquid will start to form. So yes, it is vapor, but we're just on the verge of liquid starting to form if we remove some heat. You can look at it the other way as well. If we're adding heat, when we hit the saturated vapor line is when the very last little bit of liquid disappears and we achieve 100% vapor. So these two saturation lines are very important features of the TV diagram. So typically when we draw a TV diagram, the very first thing we show is the saturated liquid and saturated vapor lines like this, because we need to get the states that we're plotting on these TV coordinates in the right position relative to the saturated liquid and saturated vapor lines. Now, this point that we're showing in the middle of this liquid vapor region is a two-phase mixture. Remember that the general regions that we're looking at here, if we're over here, that's a liquid. If we're over here, it's a vapor. And if we're in between the saturated liquid and saturated vapor lines, we have a two-phase mixture. It's a two-phase liquid vapor mixture. So let's take a little closer look at what happens when we have a two-phase mixture. If we go horizontally from this point, which is where our mixture is sitting, to the saturated liquid line and to the saturated vapor line, and drop down from that point, the value of the specific volume at that point, remember that this axis is specific volume, the value of the specific volume at that point is called V sub F. And that is called the specific volume of the saturated liquid. Likewise, if we drop down from the saturated vapor line, this is called the specific volume of the saturated vapor. Now, just recall the state principle. It says for simple compressible substances, two independent properties are required to fix the equilibrium state. Well, the reason I'm reviewing this state principle is to expand on why this word independent is there. Two independent properties are required to fix the equilibrium state. Well, the issue here is that if we're inside the liquid vapor region, P and T are not independent. So let's take a look at this. This is a line of constant pressure on TV coordinates. So that's the experiment we did. We traced out a line that looks like that. So if I were to tell you that the pressure is, let's say, 1 bar, and I were to tell you the temperature was 99.63 degrees Celsius, those two particular properties, it's two properties, but it's not enough to fix the state, because those particular values of pressure and temperature correspond to this region here. So everywhere along that red line, the pressure is 1 bar, and everywhere along that red line, the temperature is 99.63. So those two properties are not independent in the liquid vapor region. That means for any particular value of pressure, there is only one possible temperature for that to be. And that's a consequence of this line being horizontal, of there being no temperature change during the phase change. So when we're inside the liquid vapor region, pressure and temperature, even though it's two properties, is not enough to fix the state because they're not independent. So let's take a closer look at this mixture, because we need another way to tell where we are along that line. So that's essentially the problem. We need a way to locate where we are in this liquid vapor mixture region. Are we on the saturated liquid line? Are we on the saturated vapor line? Or are we partway in between? And if so, where? So remember we said that if we drop down from this point, this is Vf, the specific volume of the saturated liquid. Whereas if we drop down from this point, that's Vg, the specific volume of the saturated vapor. Well, let's take a look at how this relates to what's going on in a mixture. So here we have a mixture, liquid and vapor. Well, if we were to go inside of this piston cylinder device and grab a chunk of this vapor and measure its specific volume, we would find it would be equal to Vg. So the specific volume of saturated vapor is the specific volume of the vapor when we have a mixture. Likewise, if we were to go into the bottom of this piston cylinder device and grab a chunk of this liquid and measure its specific volume, we would find it would be equal to VF, the specific volume of the saturated liquid. So whenever we have a mixture, the liquid in that mixture has this value of specific volume, and the vapor in that mixture has this value of specific volume, regardless of where we are between these 2 points. So all of these mixture states, the liquid would have the same specific volume and the vapor would have the same specific volume. The way that we tell the relative amounts of liquid and vapor then is from a new property called quality. And quality, the symbol that we use for quality is a lowercase x. So from now on, when you see a lowercase x, that is the quality. And the way it's defined is the mass of the vapor over the total mass. So it's a mass fraction. Quality of 0 means there's no vapor. Quality of 1 means it's all vapor. And anywhere in between, we have a mixture. So remember, quality is a mass fraction of vapor. Now, we want to take this idea of the specific volume of the saturated liquid and saturated vapor and the quality and talk now about the specific volume of the mixture. So, the way specific volume is defined is volume divided by mass. So the specific volume of a mixture is the total volume of our mixture divided by the total mass of our mixture. That's the definition of specific volume. Well, let's just consider a kilogram of mixture. So that piston cylinder device that we were looking at, imagine that the total mass inside of there is 1 kilogram. This expression gives us the specific volume of the mixture, which is the left-hand side, as a function of quality. We see quality here in 2 different places, and the specific volume of the saturated liquid right there, and the saturated vapor right there. So we can get the specific volume of the mixture from those 2 values, VF and VG, and from the quality. Now let's see how this equation works, why it looks like it does. Looking first of all at the first part, remember we have 1 kilogram total inside of this thing. So that means the mass of the vapor is x kilograms. So 1 kilogram total, the fraction which is vapor is x. So there are x kilograms of vapor inside of our little piston cylinder device where we got vapor floating around there and liquid in the bottom. So x is the mass of the vapor on top. Well, if we multiply that by its specific volume, which is Vg, we get the volume of the vapor, right? This is mass, kilograms. This is cubic meters per kilogram, specific volume. So this will be the volume of the vapor. Likewise, the second term gives the volume of the liquid. So if there are x kilograms of vapor in this mixture, then there are 1 minus x kilograms of liquid. So this part in parentheses, 1 minus x, is the mass of the liquid laying in the bottom of this container. We multiply it by the specific volume of the liquid to get the volume of the liquid. And so 1 minus x times VF is the volume of the liquid laying in the bottom of the container. And of course we add the 2 together, we get the total volume, and that is a specific volume because the total mass is 1 kilogram. So this equation tells us something about the mixture, in this case the specific volume, from the quality and the specific volume of the saturated liquid and saturated vapor. Now, typically we would rearrange this equation into a little more compact form where the quality only appears in one spot. So a more common version of this equation is specific volume, V, is equal to VF plus X times VG minus VF. And you compare these 2 equations, you can see they're the same thing. Now here we have this same equation just rearranged and solving for quality. Okay, so I have quality on the left is equal to V minus VF divided by Vg minus Vf. And here we have our little illustration of Vf, Vg, and the specific volume of the mixture. So here's our two-phase mixture. We're sitting at that point. It has a particular specific volume equal to this. So the quality of the mixture is essentially this distance divided by that distance. So V minus VF is this distance, and VG minus VF is that distance. So it will range from 0 there to 1 there. So note that the quality is always between 0 and 1. You can never have a quality less than 0, and you can never have a quality greater than 1. Next thing we want to talk about is the critical point. So we've seen this sketch lots of times. We show a line of constant pressure here slicing through our liquid vapor region, VF and VG. Well, as we go to higher and higher pressures, VF gets bigger and VG gets smaller until at the critical point, VF is equal to VG. So that's an important thing that happens at the critical point. VF and VG become the same. Now, above the critical point, there really is no distinct coexistence of liquid and vapor. So we've got used to seeing containers here so far, where if we have a mixture in here, the liquid is on the bottom and the vapor is floating around on the top. But if we're above this critical point and we were to look inside of the container, we would never see this distinct interface here. We wouldn't see liquid laying on the bottom and vapor on top. It would just be a cloudy soup the whole time. The top and the bottom of the container wouldn't look any different. Okay, so above the critical point, there's no distinct coexistence of liquid and vapor. It's essentially all vapor above the critical point. So if we look at a few different lines of constant pressure here, we have our saturated liquid and saturated vapor lines shown. We've seen lots of lines of constant pressure so far where the pressure is less than the critical pressure. And so P less than P critical, line of constant pressure looks like that. And the most important characteristic is it has this flat spot in it where the phase change is occurring. But as we go to higher pressures, eventually we get to the critical pressure, and that's our line of constant pressure that goes right through the critical point. And if we go to even higher pressures, then there is no flat spot in that curve. So notice, less than the critical point, we have this coexistence of liquid and vapor as a mixture inside of our container, but above the critical point, there might be a little bit of a change in slope here depending on how close we are to the critical point, but there is no flat spot in this curve. So there is nowhere along that line of constant pressure where we have a distinct coexistence of liquid and vapor. So if we were to imagine doing our constant pressure experiment again, but with a very, very large weight on here, so that we are above the critical pressure in here, we could watch inside of there as we move along this line, and we would never see a layer of liquid on the bottom and vapor floating on the top. We would not see that coexistence. We would go from a low specific volume substance, and it would continually increase up to a higher value, but we would never see two distinct phases that have different individual specific volumes. So that's what happens above the critical point. Now, we want to do another experiment to help us see what the shape of this PvT surface is. So this we'll spend not nearly as much time on, but we're going to do a constant temperature experiment now. So before we did a constant pressure experiment, now we're going to do a constant temperature experiment. So the way we might achieve this, and what you're going to be doing in the lab actually later on in the term, is with a constant temperature bath. So we take a little piston cylinder device and we put it in a big pool of water that holds its temperature constant. Now we're starting off this experiment with a liquid. We're not going to bother looking at what happens to solids. We're starting off with a liquid, and because we're holding the temperature constant, we're going to measure the pressure and volume. So temperature is now constant, and we're measuring pressure and volume as this experiment goes on. So we're going to begin with a liquid as is shown here, and what we're going to do is grab this connecting rod and move it that direction. So we are increasing the volume, the bath is keeping the temperature constant, and we're going to monitor the pressure as we do that. So here is our PV diagram now. Remember, temperature is constant, so the other two properties are pressure and specific volume. So we're going to be tracing out a line of constant temperature on PV coordinates. Now our starting point here is at a relatively high value of pressure and a low value of specific volume. So we're starting off with a liquid in that container, and we're going to start to increase the volume. So when we have liquid inside a piston cylinder device and we increase the volume, the pressure drops very rapidly. So the first thing that we would see happen here is a rapid decrease in pressure. So it moves a tiny little bit to the right, but hardly at all. Now, that's going to continue to happen until the pressure inside of that piston cylinder device reaches the saturation pressure, at which point vapor is going to start to form. So there we have a two-phase mixture. So as we continue to increase the volume, so increase the volume of our piston cylinder device, we're going to get a two-phase mixture, and during that phase transition, temperature and pressure are going to hold constant. So this is now called the saturation pressure, corresponding to whatever temperature we're doing this experiment at. Eventually, all of the liquid inside that piston cylinder device is going to disappear, and we have 100% vapor again. As we continue to move to the right, or continue to increase the volume of this substance, the pressure is going to start to drop again. Only now we have a vapor, so the pressure drops much less quickly than it did back here where we had a liquid. So this is a line of constant temperature on a PV diagram. And if we were to redo that at a higher temperature, or a higher temperature still, we would see similar shaped lines that would look like this. So notice again, we're seeing a locus of points that are the saturated liquid line, and another locus of points over here that are the saturated vapor line. So we can join those together and we see a saturated liquid and a saturated vapor line. So this region is liquid, this region is vapor, and this is a liquid vapor mixture. So saturated liquid line on the left, saturated vapor line on the right, and of course critical point at the top, the same as before. So now if we go back to our PvT surface, essentially what we've done is we've looked at this surface from two different directions. The first experiment we did, we were looking at this surface from the top because our coordinates were T and V, and we traced out a line of constant pressure. Now this second experiment we did, we were looking at this surface from the left because our vertical axis was P and our horizontal axis was V. So we've been looking at this surface from two different directions. So what the surface actually looks like is this, and this is just a figure out of your textbook as reference there. So let's take a look at this more complicated picture here, which is a 3D image of the equilibrium surface. So first of all, notice that our axis is pressure, temperature, and volume, the same as what we were talking about earlier. The critical point is right here. This is our saturated liquid line right there. This is our saturated vapor line right there. In between them we have our liquid vapor mixture region. To the left side of the saturated liquid line we have the liquid region. To the right side of the saturated vapor line we have the vapor region. Now this PvT surface also shows the solid region. So there's solid over here, solid vapor mixture, solid liquid mixture. We're not actually interested in any of those things. The parts we're interested in are the liquid vapor mixture, and the vapor region. We're not going to be looking at solids at all in this class. Another feature of this PvT surface that I'll just point out is the triple line. So anywhere along this triple line right there, we actually have all three phases in equilibrium at the same time. So liquid, vapor, and solid are all in equilibrium at the same time along that triple line. So sometimes when we draw a PV diagram, for instance, we'll show that triple line down at the bottom of the PV diagram. So it just joins the saturated liquid and saturated vapor lines down here at the base. So that's called the triple line. Now we've looked, if we look at this, we've looked at this view of this surface from the top. We've looked at this view of this surface from this side. So a natural thing to ask ourselves is, what does it look like when we look from the third direction? What if we look from that direction? What do we see? Well, we would see then a PT diagram, right? Our vertical axis would be pressure. Our horizontal axis would be temperature. Now, of all three of these diagrams, this is the one that is the least useful for the types of problems that we're going to do. And the reason for that is that liquid vapor region, which we're very interested in for this class, really doesn't appear in a useful way in a PT diagram. That whole liquid vapor region that we've been talking about a lot lately, that whole liquid vapor region lies on this line. So that liquid vapor dome, we're seeing just the edge of it. We have to look at it from this direction to see it. On a PT diagram, we just see the edge of it. So the top here is a critical point. Down at the bottom here is essentially an end view of the triple line, which is called the triple point. And there's a similar line that heads up this way that separates the solid and liquid region. So this is also a two-phase mixture region between solid and liquid. So if we're on this line, we have a mixture of solid and liquid. If we're on this line, we have a mixture of liquid and vapor or gas. And likewise, if we're on this portion, we have a mixture of solid and gas or vapor. So the lines are the mixture regions, and the regions that they separate, or the zones that they separate this whole PT area into, are the three phases: solid there, liquid there, and gas or vapor here. So this is probably the last time we'll see a PT diagram, just because we can't really see what's going on in the liquid vapor region from this particular set of coordinates. And that goes back to our problem that P and T are not independent variables when we're in the liquid vapor mixture region. Now, we've been focusing exclusively on three properties: pressure, specific volume, and temperature. But it's important to realize that our other thermodynamic properties, for example, internal energy, enthalpy, and entropy, can also be defined as functions of two other properties. So U could be found if we know PV, for instance. H could be found if we know TV. Now, there's nothing special about those particular properties. The point here is that given any two independent properties, you should be able to find any other property you need. Said another way, given any two independent properties, you should be able to fix the state.